So what I'm going to talk about now is a little bit of the physics of the fluid flow in tight fractured reservoirs, which is very important in leading up to how we're going to apply this decline curve concept. So in unconventional reservoirs, what is it that makes the play unconventional? Well, I think we all understand it's very low permeability and lots of it. In order to get economic wells to flow from this sort of resource, we require a very large network of fractures to expose a large area to the formation. And this usually results in long-term linear flow. Let's compare a picture view of fluid flow in a conventional reservoir versus an unconventional reservoir. On the left-hand side, we have a conventional a well in a conventional reservoir. This is a vertical well. This well could be fractured as well, but usually the fracture is going to be small in comparison to the drainage area that we're dealing with. So what we tend to see is radial flow. And radial flow just means that all the flow is coming in sort of like spokes of a wheel in towards the center. And this is the flow regime, the primary flow regime that we expect to see in either fractured or unfractured vertical wells in conventional reservoirs. The key thing here is that the transport mechanism is the porous media itself. In other words, all of that fluid is flowing through the permeable reservoir towards the sink or well located in that drainage area. And the pressure drawdown is localized near the well. In contrast, unconventional reservoirs are entirely different. We have this network of fractures that exists inside the rock, and the expected flow regime is not radial anymore. Now it's linear. And the reason it's linear is because the matrix permeability is so tight that you're simply not going to get any molecules of gas or oil to flow very far within the matrix. So the only flow that we're really going to be able to get is within the fracture system itself. Let me give you an example of this. If we move just, say, 200 feet or so away from this fracture face in a reservoir that's got hundreds of nanodarcies of permeability, as opposed to, say, millidarcies of permeability, it may take literally hundreds of years for that molecule of gas to flow that distance of 100 feet. So we're not going to really get any pressure drawdown anywhere in this reservoir except very close to the fractures. So all of the flow is going to be into the fracture face, which means we get linear flow. The transport mechanism here is, of course, the fractures themselves. So this is very different when we compare it to the conventional case where the transport mechanism is the porous media. And then finally, the pressure drawdown now is distributed throughout the stimulated rock volume. When we talk about the stimulated rock or stimulated reservoir volume, we're talking about all of that reservoir that has basically become contacted by those fractures. And again, that volume of reservoir could be quite small because if we move too far away from the fracture face, we're really not causing any pressure drawdown because the permeability is so low. So understanding what that stimulated reservoir, stimulated rock volume is of course of critical importance to understanding the reserve potential or recovery potential of an unconventional reservoir. Let's talk a little bit about the linear flow properties because this is tremendously important to the long-term performance of these wells. Many of these wells exhibit linear flow that goes on for a very long time, so we need to understand what those linear flow properties are telling us. I think if there's one thing that can be said about linear flow is that it is a very non-unique flow regime. For instance, we cannot tell from well performance whether we have a series of fractures, say something like this picture here, or one long planar fracture. And I mean, we can argue all day about whether we have one or the other. At the end of the day, what is really important is that total fracture area. That's what's going to cause the production performance. That's what's going to give us the productivity of the well. So it doesn't really matter during the linear flow period where those fractures are. What really matters is how much total fracture area we have. So this system is equivalent to this system. In other words, the sum of multiple non-uniform fractures is equivalent to a single planar fracture. In addition, we have a non-uniqueness between the total fracture area and the permeability. These two come as a pair. So the total cross-sectional area to flow, AC, multiplied by the square root of permeability, is the parameter that we're going to be able to determine. But we cannot determine uniquely the permeability or the total cross-sectional area to flow in the fracture. So one of these two has to come from an independent estimate. We cannot get both of them from well performance analysis, only the product of the two. So what this means is that we could have a system like this with a long fracture and low permeability, and effectively that is equivalent to a system like this that has a short fracture and higher permeability. And so we use this concept of equivalent permeability, which equates the two ratio of the areas, total fracture areas of these two cases, and the permeability. So let me talk a little bit about this simplified approach. We're going to use a combination of some analytical and empirical methods to assess what's going on in that reservoir. And at the end, we're going to use decline curves to determine a long-term production forecast and expected ultimate recovery, the same way that we do with conventional reservoirs, but with an unconventional approach. We're going to start out by looking at a log-log plot. And Wattenberger and his colleagues really spent a lot of time developing methodologies for doing this. And this is going to help us see the flow regimes. Arguably the most important step in the analysis is understanding the flow regimes that we're observing from the well performance data. Once we understand that, we can use the analysis plots to extract what we call bulk parameters. And the bulk parameters are these cross-sectional area, square root K, product, and stimulated rock volume, skin, things like that. We're going to be able to extract those from the analysis plots. And then finally, the forecast is going to come from using modified hyperbolic decline curves. Now we're going to show how this all ties together as we go through. To start out with, let's look at linear flow theory. And what we're looking at here is a single fracture, and the fracture is intersecting a horizontal wellbore. The fracture is shown here in sort of three-dimensional view, and at the bottom in plan view. The equation that describes linear flow is PD is equal to square root of pi TD. This is for constant rate. If we're dealing with constant pressure, we have a similar equation to this that's just offset by a constant. So it makes it quite convenient because linear flow has the same form in constant rate as it does in constant pressure. It's just offset by a constant multiplier. When we turn this into a dimensional equation, there are two standard equations that are important. One of them is expressed in terms of pressure, or in this case pseudo pressure because we're dealing with gas. And that's where we have delta P over Q. And that is a straight line or straight line equation in terms of square root of time. And then the other one is expressed in terms of production rate, which is just an inverse of the first equation. And then we have the square root of time on the bottom. It's no longer a straight line. It actually becomes strongly hyperbolic in terms of square root of time. So both of these are useful in different ways, and we'll talk more about that in a few minutes. The m in both of these equations is a function of the AC root k, which is that characteristic parameter related to the total fracture area and square root of permeability product. And that's really going to be the driver of the productivity of all of these unconventional fractured wells. They all basically have the same sort of behavior. So you'll notice that the m in the first equation is the coefficient to the square root of time. And we can actually plot, if we do a plot of delta P over Q versus square root of time, we're going to see that the slope of that line is the m, and that's going to give us the A root K. We'll get to that in just a minute. The other thing that's of interest is if we do a logarithmic plot, or log rate versus log time, we'll see that a half slope appears when we have linear flow. If we go back and look at this again, that comes directly out of this equation. And Wattenberger showed this. This is an example from a paper that Wattenberger and his colleagues did quite a few years ago from a vertical, tight fractured gas well. And the interesting thing about this example is that this is almost 20 years of production data. And we see we have linear flow for the whole period. So this makes it very clear that linear flow is a dominant characteristic in these tight plays. And that's where we're going to expect to see this half slope on the log-log plot. So the log-log plot is very useful as a diagnostic plot for identifying linear flow, and we're going to see a half slope when we do that. The other component of this that is very important is the flow within the fracture. So far we've been talking about flow into the fracture face itself, and that's the linear flow part where we're going to see the dominant transient flow characteristic in the data. However, there is also a component intrinsically in the fracture. And in fact, this is the flow that occurs first and foremost in the production. The interesting thing is that it appears that this flow regime is over, the transient part of it is usually over fairly quickly. So in a daily production data sense, the transient flow intrinsically in the fracture is not going to last very long. However, it does leave somewhat of a footprint, so to speak, behind in the form of this B prime. And this B prime is simply a pressure loss that is experienced as the fluid flows through this fracture system. Remember, we said that the transport mechanism in unconventional reservoirs is the fracture system itself. So as the gas or the oil flows from the tip of the fracture to the perforations on the wellbore, it's going to experience this pressure loss delta P. Interestingly, it appears from observation that the transient effect of that pressure loss is gone quickly, as I said before, but there's a steady state pressure loss that's left. And that delta P acts like a skin damage. So that's what we're modeling here with this B prime. It's a pseudo skin or apparent skin that acts on this fracture. The source of this skin is most likely due to finite conductivity in the fractures. We all know that these fractures are not infinitely conductive. They do have some resistance to flow. And so that finite conductivity in the fracture system is going to cause that B prime to appear. If we have a low conductivity in the fracture system, that B prime could be quite large. If we have a high conductivity in the fracture system, then that B prime could be much smaller. However, there are a whole number of other items that may be rolled up inside this delta P, and we have no hope as reservoir engineers of being able to distinguish between these different things, these different phenomena. All we can do is say that the whole thing as a bulk parameter acts as this B value. And that's really all we're seeing. We're not seeing the individual transient effects of all of these. We can roll them all up together as this total skin or B prime value that exists in the data. And it turns out that this B value is very easy to see in production data. It's one of those things that we can, just by looking at a plot, we can distinguish very clearly how much apparent skin there is. For instance, if we look at a type curve plot, and this is now constant pressure, log production rate versus log time, what we'll see in the presence of no skin at all is a perfect half slope, as I showed you in Wattenberger's example earlier. However, if we start to impose a skin damage effect, either a weak one or a strong one, we're going to see various different levels of masking or hiding of that half slope. When we see the skin is equal to 1, the half slope is almost non-existent because it's been replaced by this flat effect because of the skin. So it has a pronounced effect on the log-log plot, and we may not be able to see our characteristic half slope in the data when we have this skin effect in place. However, if we do a square root of time plot, so this is a plot of delta P over Q, or for constant pressure cases, simply the inverse of flow rate versus square root of time, the linear flow is still going to be apparent even in the presence of skin. And we can see the effect of skin as basically as the position of this line changes. So if there's no skin, then this line will go through the origin. If there is a apparent skin there, then this straight line will not go through the origin. It'll have a positive y-intercept. And the value of that positive y-intercept is proportional to how much apparent skin damage there is. So we can very, very quickly categorize our wells as being either damaged or efficient producers. And you can think of this skin as a completion efficiency in a sense. The higher this number is, the less efficient the completion is. And it's not necessarily related to the total fracture area, but it's related to the conductivity of the fractures themselves. Here's an example of some real production data plotted on a square root of time plot. And as we can see in this case, the intercept is positive, which would indicate that we have some damaged skin in place for this well. The slope of the line is what's going to give us the A root K, or the product of fracture area and square root of permeability. And we can see that those two characteristics are independent of each other, and both can be easily determined from this plot. So the square root of time plot really gives us two separate parameters. One of them is the bulk parameter A root K, and the other one is this apparent skin. Let's look at what we call now the simplified model. The simplified model says that in reality we may have many of these fractures crisscrossing all over the place inside this stimulated rock volume. We don't really know where these fractures are, and really we don't necessarily care. For the purposes of production forecasting, it is perfectly adequate and valid to say that this system can be represented by this simple system where we have no fractures, just a homogeneous box, so to speak, reservoir with an equivalent permeability that takes into account that there's fractures in this system. Now this works just fine, provided that these fractures are relatively uniformly distributed throughout the stimulated rock volume. If there's significant heterogeneity to how these fractures are distributed, then there'll be a divergence between these two solutions. But if we can assume that there's relatively uniform distribution and it's a homogeneous fracture network, we can easily replace this system, which is the real system, with this proxy model, which assumes that we have a basically homogeneous system with an equivalent permeability. And we make these two systems equal using this concept that A root K has to be constant for both of these systems. And the equivalent permeability is now the effective permeability within that stimulated rock volume. Let's talk about the time to end of transient flow. We've talked about this linear flow, but linear flow doesn't go on forever. At some point in time, the linear flow will stop. And in a conventional reservoir, we would think of that as being reservoir boundaries. And for the time being, we'll use that same definition. In a minute, we'll expand on that a little bit further. But let's just assume that this box, this stimulated rock volume, has a limited extent. How do we determine the drainage volume or drainage area? And specifically, how do we determine how long it takes to reach those boundaries? Because that's going to become very important in determining the expected ultimate recovery for the well. Wattenberger has come up with a formula that can tell us the time to end of transient flow. And this concept is very similar to the radius investigation concept. But in fact, it doesn't require permeability because remember, there's a consistency between permeability and the total fracture area. So in fact, all we need to know is really the slope of that line on the square root of time plot, which is that m value. And once we know that, and if we can provide a drainage area, then we can determine the time to end of transient flow. So this number is going to become very important to our production forecast. Now the real question is how do we find out that drainage area? Again, if we refer back to that plot or back to that equation, we can get M from the data, but we don't have AD. We don't know what our drainage area is. So in a conventional reservoir, the drainage area is really defined by the volumetrics of the reservoir. It's defined by interwell interference, and it's defined by things like reservoir pinch-outs and faults. And we can define a boundary system that drains from the outside in towards the well, as we showed before. In an unconventional reservoir, we're never going to see the outer boundaries. The permeability of this matrix rock is just too low, at least in the sorts of developments that we have in the industry right now. As we start to get into much more dense drilling spacing, we may start to see interference. But certainly in the year 2010, 2011, we don't really have interwell interference in unconventional completions. So what we see instead is it turns out we still do see what I'm going to call apparent boundary dominated flow, because it may not be fully boundary dominated flow, but we still do see it, and it's not from outer boundaries draining, it's actually from inner boundaries caused by the interference between fractures in a multi-fractured horizontal well. So when we have a horizontal well with multiple fractures, those fractures will eventually interfere with each other, and that's what's causing our apparent boundary dominated flow. And you can see there's two examples of this here. One where we have just a slab fracture model or parallel transverse fractures, and the other one where we have parallel and orthogonal fractures. In this case, the boundaries actually are completely sealing in these matrix blocks, and this would be pure boundary dominated flow. In the case of just parallel fractures, it would be apparent boundary dominated flow because we're still getting influx on the tips of the fractures. In any case, both of these cases are going to show a signal at some point in time in their well performance that indicates a transition to boundary dominated flow, and that signal, that indication, is going to give us some sense of the size of the stimulated rock volume. This is very different from the conventional case, in which boundary dominated flow gives us a sense for the size volumetrically of the reservoir. These are very different attributes. We have no hope of assessing the volumetric size of the reservoir in an unconventional reservoir. In fact, the volumetrics of unconventional reservoir tends to lose any sort of meaning whatsoever. What really matters to reserves and recovery is that stimulated rock volume and nothing more. So what we're really interested in is how big that stimulated rock volume is. We don't really care so much about how big the total drainage volume is in the whole system, because we're never going to see those boundaries. Just to give you some sort of idea of how long it may take to reach boundary dominated flow in different matrix permeabilities. This is the time to Wattenberger's time to stabilization calculation, or time to end of transient flow calculation for matrix permeabilities of 100 nanodarcies, 10 nanodarcies, and 1 nanodarcies. And we can see that in as early as 3 days, we may start to see apparent boundary dominated flow if we have fractures that are close enough together. And in many cases, we may have fractures that are that closely spaced. In other cases, we may have fractures that are much further apart. But we can see it is very reasonable to expect that within the first year or 2 years, we may start to see apparent boundary dominated flow in many of these horizontal multi-fract completions. In vertical wells with single stage fractures, much less likely that we're going to see boundary dominated flow, which is why Wattenberger's example that we looked at earlier didn't show the boundary dominated flow at all in 20 years of production. In a multi-fract horizontal case, we're much more likely to see it sooner, especially since in completions we tend to be pumping more and more stages of fractures in a limited lateral length. So to assess this boundary dominated flow, we have a tool that we've been using for years in RTA that's called the flowing material balance. It works on the principle of pseudo-steady state. I won't go through all the details of that, but I'll show just very quickly pictorially what this means. The principle of pseudo-steady state says that the rate of depletion of the average reservoir pressure is the same as the rate of depletion of the pressure measured at the wellbore of the sand face. So if we can measure dp dt at the sand face, then we know how fast the reservoir pressure is depleting. In this case, this would be the average reservoir pressure within the matrix blocks. And the rate of decline of that pressure is going to tell us essentially, or is going to be proportional to the size of that stimulated rock volume. And so we're going to use the flowing material balance, which is a plot of normalized rate versus normalized cumulative production. And the intercept, or the extrapolation of that plot, is going to give us that hydrocarbon pore volume. And so there's an equation that can help us put all that together, which is well known in the industry already. And the key thing, or the key feature here, how this relates back to our linear flow analysis, is that this flowing material balance can provide us this drainage area that we've been looking for. So if we extrapolate this flowing material balance plot down to the x-intercept, it gives us a hydrocarbon pore volume and gives us a drainage area that we were looking for in Wattenberger's transient equation. Let's relate this back now to the square root of time plot. And we can see, if we use that same data set, that we have an early period here. The dotted green line now is the time to end of transient flow. That's calculated based on the original gas in place that was calculated from the flowing material balance plot. And so those plots now relate together. What we can also see very clearly is that shortly after that point in time, we get a departure on the square root of time plot. The data on the square root of time plot departs from the straight line. So the appearance of boundary dominated flow is very shortly followed by a departure of the data from the curve, and it's easily recognizable. Once we have enough data beyond the onset of boundary dominated flow, we can very clearly see that we are no longer in pure transient linear flow, and we have in fact started to see all of those interior interference boundaries within the stimulated rock volume. So this is an important event to try and recognize in our unconventional reservoirs, is this departure from straight line linear flow into some sort of apparent boundary dominated flow. What happens if boundary dominated flow is not observed? Well, this is a case that may come up very frequently, particularly if we're only looking at a few months worth of production data. So if we look at the top two plots, here's an example. This is a square root of time plot. The green dotted line is determined based on the extrapolation of the flowing material balance plot. And the problem with this interpretation is that if we look at this data, it's obviously purely transient linear flow. So the dotted green line doesn't belong here. Our extrapolation using the flowing material balance is too pessimistic. What in fact we need to do is extend this extrapolation, in other words, make the drainage area larger, and by doing that, make our time to end of transient flow progress further so that in fact it's sitting at the end of the data, and that's where we need it to be. In reality, in a case like this, we don't know when the end of transient flow is. And this is one of the single biggest problems with tight and unconventional resources. And the reserves community has a huge issue with trying to tackle this problem. And this is something that, is always going to be an issue. We have this inherent uncertainty in these unconventional and low permeability plays because we simply have not seen the boundaries of the system yet. So if we're talking P90 reserves, we really have to put that dotted green line right at the end of the data, and that's going to tell us the assumption here is that the boundaries are reached right now, which of course is not true. We don't know when the boundaries are going to be reached, but this represents a minimum original gas in place within the stimulated rock volume, which can then give us a forecast which I think would be consistent with a, say, P90 or proved reserve scenario. The picture shown on top is probably going to be too pessimistic because it's assuming that boundaries were reached way back here when it's clear that we're still in transient flow even beyond that point in time. So it's important to use these two plots together and get some sort of consensus as to what we believe is going on. The square root of time plot is going to show us our linear flow and is going to indicate where the transition from transient to boundary dominated flow is occurring. The flowing material balance plot is going to provide us with an extrapolation of the drainage volume or the stimulated reservoir volume. And these two used together can help us get a sense for that those reservoir characteristics that are going to provide our forecast. All right, now let's tie all this together. What have we done so far? So far we have determined the A root K and the skin from the slope and the intercept of the square root of time plot. We have also determined the drainage area from the flowing material balance plot. Again, keep in mind that this drainage area may be a non-unique number. If all we see is transient flow, then the drainage area is simply going to be the minimum drainage area, and we get that by putting that dotted green line at the end of the data. Let's take an arbitrary case here and talk about how we could generate a production forecast that's consistent with those properties. So once we have the A root K, the skin, and the drainage area, we actually have everything we need to generate a production forecast. And to make matters simpler, we can actually package this up into a modified hyperbolic decline, which is nice because it's the language that the reserve auditors speak anyways. It's something that the industry is already familiar with the form of these curves. So there's no reason to change the language with which we forecast well performance. It's just that we're going to use decline parameters that are a little more scientific and have a basis in the real physics of the problem, rather than being assumed from some analog or some other sort of assumption that isn't really defendable. So what we're going to do is a modified hyperbolic, where we have a hyperbolic decline curve at the beginning, and then where that dotted green line is, in other words, where we transition from transient flow to boundary dominated flow, or that time to end of transient flow, that is the critical point in that forecast, because now we're going to transition at that point to a lower hyperbolic. So we have a high hyperbolic transitioning to the lower hyperbolic at that point in time. So rather than that occurring at a limiting decline rate, we're going to have it occur at the end of transient flow, which is now related to the drainage area. So that time to end of transient flow is related to the drainage area. It's also related to the M, which is the A root K. So a lot of the different well performance characteristics come into assessing where that end of transient flow is going to occur. Let's talk about the first decline curve. The first decline curve, as it turns out, since it has this form here, this is the analytical form of linear flow. It turns out that this is almost exactly the same as an ARPS hyperbolic decline curve with the b value set to 2. So if we take the ARPS hyperbolic equation and set the hyperbolic exponent to 2, essentially we get linear flow. So I mentioned earlier that we should not use the hyperbolic exponent as a curve fitting parameter, and this is the reason why. The b value of 2, or the hyperbolic value of 2, is really the only hyperbolic exponent that makes sense in transient flow for fractured wells. So we're going to use that hyperbolic exponent of 2 prior to the end of transient flow, and then once we see the end of transient flow, we're going to transition to a lower b value. And what b value we use after that dotted green line really depends on how we think the boundary dominated flow is going to occur after that. And this depends on many different factors. For example, it depends whether it's an oil well or a gas well. If it's an oil well, the b value will be somewhat lower, maybe 0.1 to 0.3 for solution gas drive. If it's a gas well, evidence shows that the b value could be higher, as high as b value of 0.5. And the reason for this is the variable gas compressibility with pressure. The b value, in fact, could be even higher than 0.5. If we have boundary dominated flow of a heterogeneous, a highly heterogeneous system. In other words, a system where we have non-uniform distribution of fractures or heterogeneous permeability, which amounts to the same thing, the B value could be even higher than this. In fact, it could go as high as 0.8 or 0.9. So we have control over the B value that we use in the second period, basically relating to how we think the boundary dominated flow is going to occur and what fluid is in place that we're draining. The B value prior to the end of transient flow is going to be set and locked into a B value of 2 because that's linear flow. And really it's as simple as that. That's how we create our decline curve analysis for an unconventional reservoir. And then to show that we have uncertainty in this interpretation, we have to generate multiple forecasts for different drainage areas. And the plot, the inset plot on the top right, is indicating that if we choose different starting drainage areas or different ADs, we get different EURs associated with those. And that's what each of these different type curves or different forecasts represent. The P90 forecast in all of these cases, or in any case that we do this work for, is going to be the one for which the green line is set at the very end of the data. That is to say, if we have transient flow and no evidence of boundary dominated flow. And then the P50 reserve would be something with an assumed higher drainage area, which could be based on well spacing or microseismic mapping or something that's going to indicate or suggest what we think that drainage volume might be. So that is really the theory and the physics of fluid flow in unconventional reservoirs. So what I'd like to do in the next section is show some examples of how we handle this in the software. And so this will bring an end to the theory part of the section, and take a look at the next video to see some practical examples of how to handle this inside the Harmony software.